Power series. Let's begin by looking at an example. Recall the geometric series. The sum from k equals 0 to infinity of x to the k equals 1 plus x squared plus x cubed and so on. We know that this series converges if the absolute value of x is less than 1 and diverges otherwise. So let's use this series to define a function f on the open interval from -1 to 1 as follows. Let f of x equal the sum from k equals 0 to infinity of x to the k, or 1 plus x squared plus x cubed and so on, for all absolute value of x less than 1. A function defined in such a manner is called a power series. Let's notice that we can think of f as the limit of a sequence of polynomials. That is, for each x, f of x is equal to the limit as n goes to infinity of p sub n of x, where p sub n of x equals 1 plus x squared and so on up to x to the n. Here's the graph of p1. That's just the graph of y equals 1 plus x. And here's the graph of p2, which is p1 plus the x squared term. Here's the graph of the cubic polynomial p3, followed by p4, and then p5. Now let's skip to p10, and then p15, p20, and p25. Notice that there begins to be very little difference between these graphs for x between -1 and 1. Here's the graph of p100, which will be quite close to the graph of the power series, that is the infinite sum, unless x is extremely close to one of the endpoints -1 or 1. Now let's remember that we know a so-called closed form for the geometric series, and so we also know a closed form for the function f of x. F of x will equal 1 over 1 minus x for all absolute value of x less than 1. So here's the graph of the function f of x, along with the polynomial p100. Notice that f has a vertical asymptote at the right-hand endpoint of its domain. It's undefined at the left endpoint -1, but it has a limit as x approaches -1 from the right. We point out that the expression 1 over 1 minus x makes sense for all x other than 1, but our power series f of x is undefined outside the open interval from -1 to 1 because the defining series does not converge for those values of x. So what exactly is a power series? Given a sequence of coefficients c sub k, as k goes from 0 to infinity, we can define a function f whose value at x is f of x equal to the sum from k equals 0 to infinity of c sub k times x to the k, or c0 plus c1x plus c2x squared, and so on. More generally, given a number x0, we could define f of x equal to the sum from k equals 0 to infinity of c sub k times x minus x0 to the kth power, or c0 plus c1 times x minus x0 plus c2 times x minus x0 squared, and so on. This is a power series about the number x0. In the first case above, we'd say that the power series is about 0. The domain of such a function is the set of all x for which the series converges. Note that a polynomial of degree n is a power series in which c sub k is equal to 0 for all k greater than n. In fact, a good way to think about a power series is that it's a kind of super polynomial that may have infinite degree. Variations on the geometric series. Closed forms for many power series can be found by relating the series to the geometric series. For example, consider the function f of x defined by the sum from k equals 0 to infinity of -1 to the k times x to the k, or 1 minus x plus x squared minus x cubed, and so on. This is nothing but the geometric series with x replaced with minus x. And so its closed form is 1 over 1 minus x, or 1 over 1 plus x. And this will converge when the absolute value of minus x, which is the same as the absolute value of x, is less than 1. Another example. Let f of x equal the sum from k equals 0 to infinity of 2 to the k times x to the k plus 2, which would be x squared plus 2x cubed plus 4x to the fourth plus 8x to the fifth, and so on. Now, we'd like to be able to think of the kth term here as something raised to the kth power. So let's notice that if we factor off an x squared, then the kth term is 2 to the k times x to the k, which is the kth power of 2x. So f of x is equal to x squared times the sum from k equals 0 to infinity of 2x raised to the kth power. That series is the geometric series with x replaced with 2x. So a closed form for that series is 1 over 1 minus 2x, which we multiply by x squared. The series converges when the absolute value of 2x is less than 1, that is, when the absolute value of x is less than 1/2. Another example. Let f of x equal the sum from k equals 0 to infinity of minus 1 to the k times x to the 2k, which is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Notice that the kth term here is simply the kth power of minus x squared. So this is the sum from k equals 0 to infinity of minus x squared raised to the kth power. And so by the closed form of the geometric series, this is equal to 1 over 1 minus x squared, or 1 over 1 plus x squared, provided that the absolute value of minus x squared is less than 1, which happens precisely when the absolute value of x is less than 1. Notice that the expression here for the closed form makes sense for all x, but it does not equal f of x outside of the open interval from minus 1 to 1. F of x is undefined there. Another example. Let f of x equal the sum from k equals 0 to infinity of x to the 2k plus 1 power divided by 3 to the k, which equals x plus 1/3 x cubed plus 1/9 x to the 5th plus 1 over 27 times x to the 7th, and so on. Again, we want to view the kth term as the kth power of something, so we need to factor off x, which makes the kth term x to the 2k over 3k, and that's the kth power of x squared over 3. So f of x is equal to x times the sum from k equals 0 to infinity of x squared over 3 raised to the kth power. That series is the geometric series with x replaced by x squared over 3, and so its closed form is 1 over 1 minus x squared over 3. So multiplying by x, and also multiplying top and bottom of the fraction by 3, gives us 3x over 3 minus x squared. And that formula is valid when the absolute value of x squared over 3 is less than 1, which happens when the absolute value of x is less than the square root of 3. Radius of convergence. Theorem. Given a power series f of x equal to the sum from k equals 0 to infinity of c sub k times x minus x naught to the kth power, one of the following is true. The series converges when x is equal to x naught and diverges otherwise, or there exists a number r greater than 0 such that the series converges absolutely when the absolute value of x minus x naught is less than r and diverges when the absolute value of x minus x naught is greater than r, or the series converges absolutely for all x. Now, in the second case, the number r is called the radius of convergence of the power series. The radius of convergence is defined to be r equals 0 in the first case and r equals infinity in the third case. The main point here is that the domain of a power series is always either a single point or an interval. If r isn't 0, the power series converges on an interval centered at x naught. That interval is called the interval of convergence. When it's a bounded interval, it may contain one, both, or neither of its endpoints, and convergence at an endpoint may be conditional. But convergence in the interior of the interval of convergence is always absolute. The radius of convergence of a power series can usually be found by applying the ratio test. However, in some cases, the root test is easier. Example. Find the radius of convergence of the power series f of x equal to the sum from k equals 1 to infinity of k squared times x to the k, which equals x plus 4x squared plus 9x cubed, and so on. We'll use the ratio test. The absolute value of the k plus first term divided by the kth term equals the absolute value of k plus 1 squared times x to the k plus 1 divided by k squared times x to the k. That equals k plus 1 squared over k squared times the absolute value of x to the first power. Now, as k goes to infinity, k plus 1 squared over k squared approaches 1, and so this quantity approaches 1 times the absolute value of x as k goes to infinity. So the ratio test tells us that the series converges absolutely when the absolute value of x is less than 1, and diverges when the absolute value of x is greater than 1. So the radius of convergence of the power series is 1. Example. Find the radius of convergence of the power series f of x equal to the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x to the k. That equals 1 minus x plus 1/2 x squared minus 1/6 x cubed, and so on. Again, we'll use the ratio test. The absolute value of the k plus first term divided by the kth term is equal to the absolute value of x to the k plus 1 divided by k plus 1 factorial divided by x to the k over k factorial. Notice that we simply omit the minus 1 to the k here because we're taking absolute values. This is equal to k factorial divided by k plus 1 factorial times the absolute value of x to the k plus 1 over x to the k, and since k plus 1 factorial is equal to k factorial times k plus 1, k factorial divided by k plus 1 factorial is equal to 1 over k plus 1. And of course the absolute value of x to the k plus 1 divided by x to the k is equal to the absolute value of x. Now as k goes to infinity, 1 over k plus 1 goes to 0, and so 1 over k plus 1 times the absolute value of x approaches 0 for any x, and 0 is certainly less than 1, and so the ratio test tells us that the power series converges absolutely for all x, so the radius of convergence is infinity. In other words, the interval of convergence is the entire real number line. Example. Find the radius of convergence of the power series f of x equal to the sum from k equals 1 to infinity of k plus 1 over k raised to the k squared power times x to the k, which equals 2 times x plus 3/2 to the 4th power times x squared plus 4/3 to the 9th power times x cubed, and so on. Here we'll use the root test. The kth root of the absolute value of the kth term is equal to the kth root of k plus 1 over k to the k squared power times the absolute value of x to the k. Now we take the kth root here by dividing each exponent by k. So we have k plus 1 over k to the kth power times the absolute value of x to the first power. The factor in front here may look a little more familiar if we rewrite it as 1 plus 1 over k raised to the kth power. And next we want to recall that as k goes to infinity, 1 plus 1 over k to the kth power approaches the number e. So as k goes to infinity, the kth root of the absolute value of the kth term here approaches e times the absolute value of x. That's less than 1 if the absolute value of x is less than 1 over e. So the root test tells us that the series converges absolutely when the absolute value of x is less than 1 over e, and diverges when the absolute value of x is greater than 1 over e. So the radius of convergence is 1 over e. Example. Find the interval of convergence of the power series f of x equal to the sum from k equals 1 to infinity of minus 1 to the k minus 1 over k times x to the k. Let's use the ratio test. The absolute value of the k plus first term over the kth term is equal to the absolute value of x to the k plus 1 over k plus 1 divided by x to the k over k. This is equal to k over k plus 1 times the absolute value of x, and as k approaches infinity, this approaches 1 times the absolute value of x. Therefore, the series converges absolutely when absolute value of x is less than 1, and diverges when the absolute value of x is greater than 1. In other words, the radius of convergence is 1. Now, since we're looking for the interval of convergence, we need to check the endpoints x equals plus and minus 1. When x equals minus 1, the series is the sum from k equals 1 to infinity of minus 1 to the k minus 1 over k times minus 1 to the k. Now, minus 1 to the k minus 1 times minus 1 to the k is always equal to minus 1, since one of those factors is negative while the other one's positive for any k. So the series is the sum from k equals 1 to infinity of minus 1 over k, which is just minus the harmonic series which diverges. If x equals 1, then the series is the sum from k equals 1 to infinity of minus 1 to the k minus 1 over k, and that's a conditionally convergent alternating series. So we've determined that the power series converges when absolute value of x is less than 1, as well as when x is 1. So the interval of convergence is the half-open interval from minus 1 to 1, including 1, but not minus 1. Differentiation and integration of power series. Theorem. Let f of x equal to the sum of c sub k times x minus x naught to the k be a power series with a non-zero radius of convergence r. Then f prime of x is equal to the sum of ck times k times x minus x naught to the k minus 1 for absolute value of x minus x naught less than r, and the indefinite integral of f of x dx is equal to the sum of c sub k divided by k plus 1 times x minus x naught to the k plus 1 plus an arbitrary constant c for absolute value of x minus x naught less than r. Now, what this theorem is actually telling us is that a power series may be differentiated and integrated term by term using power rules for differentiation and integration, and the resulting series have the same radius of convergence as the original power series. Example. We know that 1 over 1 minus x is equal to the sum from k equals 0 to infinity of x to the k for absolute value of x less than 1. So by differentiating each side of that equation, we learn that the derivative of 1 over 1 minus x, which is 1 over 1 minus x quantity squared, is equal to the derivative of the right-hand side, which is the sum from k equals 0 to infinity of k times x to the k minus 1. By a shift of indices, that series is the same as the sum from k equals 0 to infinity of k plus 1 times x to the k, and this formula is valid for all absolute value of x less than 1. On the other hand, if we integrate both sides, or rather anti-differentiate both sides, we find out that minus the natural log of 1 minus x is equal to the sum from k equals 0 to infinity of 1 over k plus 1 times x to the k plus 1 plus a constant c. Now we can determine the value of c here by evaluating both sides at x equals 0. When x is 0, the left side is minus natural log of 1, which is 0. Every term of the series there is 0, and so c must be 0. Now, by shifting the summation index by 1, we have that minus the natural log of 1 minus x is equal to the sum from k equals 1 to infinity of 1 over k times x to the k for absolute value of x less than 1. Example. Let f of x equal the sum from k equals 0 to infinity of 1 over k factorial times x to the k, which equals 1 plus x plus 1 half x squared plus 1/6 x cubed plus 1 over 4 factorial x to the fourth, and so on. An application of the ratio test shows that the series converges absolutely for all x. So, for all x, we have f prime of x equal to the sum from k equals 0 to infinity of 1 over k factorial times k times x to the k minus 1. Now, k divided by k factorial is the same as 1 over k minus 1 factorial. So f prime of x is equal to the sum from k equals 1 to infinity of 1 over k minus 1 factorial times x to the k minus 1. If we write out a few terms of that series, we see that it equals 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and so on, which is exactly the same as the sum from k equals 0 to infinity of 1 over k factorial times x to the k, which was our original function f of x. So, f prime of x is equal to f of x for all x. Now, it turns out that the only functions that have that property are constant multiples of e to the x. Now, since we can easily check that f of 0 is equal to 1, we can conclude that f of x must equal e to the x for all x. So we've learned that e to the x is equal to the series, the sum from k equals 0 to infinity, of 1 over k factorial x to the k for all x. A power series expansion of the natural log of 1 plus x. Let's first note that the derivative with respect to x of the natural log of 1 plus x is 1 over 1 plus x. For absolute value of x less than 1, that's the closed form of the geometric series with x replaced with minus x. So we have the sum from k equals 0 to infinity of minus 1 to the k times x to the k for absolute value of x less than 1. Now, by integrating both sides, we have, for absolute value of x less than 1, that the natural log of 1 plus x is equal to an antiderivative of the sum from k equals 0 to infinity of minus 1 to the k x to the k dx, and that equals the sum from k equals 0 to infinity of minus 1 to the k times x to the k plus 1 divided by k plus 1 plus an undetermined constant of integration. We can determine that constant by evaluating both sides of this equation at x equals 0. The left side at x equals 0 is the natural log of 1, which is 0. Every term of the series here is equal to 0 when x is 0, and so the constant must be 0. So we have that for absolute value of x less than 1, the natural log of 1 plus x is equal to the sum from k equals 1 to infinity of minus 1 to the k minus 1 divided by k times x to the k, which equals x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th, and so on. Now we actually get something extra here. The series also converges when x equals 1, and its value there turns out to be just what it should be, the natural log of 2. So we now know that the numerical series, the sum from k equals 1 to infinity of minus 1 to the k minus 1 over k, which is our alternating harmonic series equal to 1 minus 1/2 plus 1/3 minus 1/4 and so on, is equal to the natural log of 2. A power series expansion for the inverse tangent of x. Let's first note that the derivative with respect to x of the inverse tangent of x is equal to 1 over 1 plus x squared. For absolute value of x less than 1, that's the closed form of the geometric series with x replaced with minus x squared. So it's equal to the sum from k equals 0 to infinity of minus x squared to the kth power, or minus 1 to the k times x to the 2k, for absolute value of x less than 1. So for x in that interval, the inverse tangent of x is equal to an antiderivative of the sum from k equals 0 to infinity of minus 1 to the k x to the 2k, which we compute term by term. It's the sum from k equals 0 to infinity of minus 1 to the k times x to the 2k plus 1 divided by 2k plus 1, plus a constant of integration c. And by evaluating both sides at x equal to 0, we again find that c equals 0. So our series expansion for the inverse tangent of x on the open interval from minus 1 to 1 is x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, and so forth. Now we get something extra again. This series is a convergent alternating series when x equals 1, and its value there turns out to be the inverse tangent of 1, which equals pi over 4. So we now know that the numerical series 1 minus 1/3 plus 1/5 minus 1/7 and so on is equal to exactly pi over 4. If we multiply by 4, we have a rather famous series representation for the number pi. It's equal to 4 times the alternating sum of the reciprocals of the odd positive integers. One more example. Find the exact value of the sum from k equals 1 to infinity of k squared divided by 2 to the k. The key thing to realize here is that this series is the value of some power series at x equal to 1/2. In other words, we want to find f of 1/2, where f of x is equal to the sum from k equals 1 to infinity of k squared times x to the k. And if we can find a closed form for this series, the computation will be easy. Now we know that k times x to the k minus 1 is the derivative of x to the k, so we'd like to see a k minus 1 exponent on the x. So let's factor x from the entire series and write it as x times the sum from k equals 1 to infinity of k squared x to the k minus 1. Now each term there is the derivative with respect to x of k times x to the k. So f of x is equal to x times the derivative with respect to x of the sum of k times x to the k. Now let's do more or less the same thing again. Factor x from this series and write it as x times the sum of k times x to the k minus 1. And we can recognize that that sum is the derivative of the sum from k equals 1 to infinity of x to the k. Now that would be the geometric series, except we're missing the k equals 0 constant term of 1. But since we're taking the derivative of that series, we may as well insert that constant term because its derivative is 0. That is, we may as well start our series at k equals 0 instead of k equals 1. That way we can use our simple formula for the sum of the geometric series. And now, using that closed form, we have that f of x is equal to x times the derivative with respect to x of x times the derivative with respect to x of 1 over 1 minus x, on the open interval where absolute value of x is less than 1. Now, by computing that innermost derivative, we have f of x equal to x times the derivative with respect to x of x times 1 over 1 minus x squared. And now, using the quotient rule, we have x times the quotient with 1 minus x to the fourth in the denominator, and numerator equal to 1 times 1 minus x squared minus x times the derivative of 1 minus x squared, which is 2 times 1 minus x times minus 1. Now we can factor a 1 minus x from both terms in the numerator and cancel with a 1 minus x in the denominator, and the remaining factor in the numerator turns out to simplify to 1 plus x. So we have f of x equal to x times 1 plus x divided by 1 minus x cubed for absolute value of x less than 1. Now we can evaluate our power series at any x in the open interval from minus 1 to 1, and in particular, at 1/2, we have the sum from k equals 1 to infinity of k squared over 2 to the k equal to 1/2 times 1 plus 1/2, which is 3/4, divided by 1 minus 1/2, or 1/2, cubed, which is 1/8, and that simplifies to exactly 6.